Hello, and welcome back everybody to chapter 3 and section 3 of our calculus class. No, sorry, not calculus class, of our geometry class, getting the two mixed up. So today we will be talking about the following theorems and postulates. So unfortunately, I don't think there are any names or specific names for them. And if there are, please, leave it in the comment because I definitely would like them to be named instead of like some numbers if possible. But anyhow, let's go ahead and get started just to see what we're dealing with. So here, the first part, we're just going to do a quick recap as to what happened in the last section. So the big ideas there were that if you have the following, let me just go ahead and use my pen over here. The first recap was that it takes a minimum of 3 non-collinear points to form a plane. So if you have 3 points that is going to be non-collinear, then there is, as a result, always going to be one plane, exactly one plane, that's going to contain them. Now, in the same idea, now going to maybe like say 3 dimensions to 4 dimension, it takes a minimum of 4 non-coplanar points to form a space. Okay, so that is going to be our last one, so that's going to be space. So if you can kind of see it over here, we know that from the previous statement that there is a plane that contains points A, B, and C. So you can see that plane right there formed by that triangle. So here is kind of like that scenario then. And D is going to be a point that's not on the plane. So that's what it means by 4 non-collinear plane, because there is no single plane that contains all 4 of them. Then as a result, because you have a plane and then you have a point that's not on the plane, then that whole area that contains all of them, that's what we call just space. So this is just kind of like in 3 dimension, like anywhere at all. Now going into what our chapter or section is about, here's the first postulate, and there's a name for it, so maybe I was wrong. The flat plane postulate, that's the name for this one. Okay, so here it is. It says, if point A and point B are inside a plane we call L, then AB is also going to be in plane P. And let me go ahead and change that because I see a little mistake. It should say plane P right here. So here, let me kind of reiterate by drawing a picture. Okay, so first what we're saying is that we have a plane right here. Okay, so this is my plane, and the name of that plane is going to be P. If I have a point in there, which we'll call A, and we'll have another point in there, which we'll call B, then this postulate simply says that there is a line that contains AB, which we definitely know from the previous sections, and that line is supposed to be in that plane, right? Pretty straightforward for the most part. If 2 points are on the plane, the line that contains them definitely is going to be on the plane then, okay? All right. Next is asking, is the converse of it true? So here I'm looking at the same statement, but I'm going to flip the if and then statement, and I want to know if that's true then. So that is to say, if there's a line we call AB is going to be on the plane, then is it true that point A is on the plane and point B is on the plane? Well, that hopefully is true, because if the line's on the plane, then every single point of that line should be on the plane then, A and B being those points. So yeah, definitely the converse of it is going to be true. And if anything, it's going to be pretty trivial. So now let's go ahead and look at the first theorem of this section, which is theorem 3-2. So here in the picture is the illustration of it. It says that if I have a line and it intersects with a plane, okay, so you can see in this picture right there, the line is intersecting with the plane, and keep in mind that I am going to make it so that the line is not on the plane. So that means that it is not a part of it. So it's just kind of like, imagine like say a pencil piercing a piece of paper. Then according to this theorem, that the intersection is exactly 1 point, okay, so meaning that the intersection between this line and the plane is going to be just one single point and nothing else, okay? So now, careful, this right here, the assumption is that the line and the plane intersect with each other, because it could be the case where the line and the plane, they don't intersect each other. So for example, you have a plane right here and the line is right above it, and this is looking at it in 3D perspective. So we're not saying this scenario, but rather the line is going to intersect it, and the result is that the intersection is going to be a plane then. It's going to be a single point. So now what we're going to do is we're going to write a quick proof for it just to show that this is true. Well, here is what we can do. We can go ahead and introduce, okay, a line inside plane P. Okay, so we're going to go ahead and introduce a line inside plane P, and let's go ahead and give it a name. Let's go ahead and say that it's called line R for right now, okay? And I don't want to just introduce any line R. I want to make sure that line R intersects with line L, okay? So here, introduce a line inside a plane P, we'll call it line R, such that line R intersects with line L. Okay, and I can do that because look, if you have a plane, there are infinite number of lines that you can create. And definitely one of them is going to intersect with this line L, because if the plane intersects with the line, then the line is going to intersect with it as a result. So, we could choose one that's going to intersect with it. So here is basically what we're grabbing. Okay, so here is an example of it. So here is going to be line R right there. Are there more than one line R? Yeah, definitely. I can go ahead and choose one that's over here. I can choose one that's over here, and so on and so on and so on. There are infinitely many number of lines that's going to intersect with this line L. So if that's the case, then hey, look, I have chosen a line, right, that intersect with the line that I have. And according to Theorem 3.1, which was actually in the previous section, if you have two lines that intersect, their intersection has to be a single point. So right there, that's going to be our proof then. So we can say by Theorem 3.1, okay, there is exactly one point that is the intersection between line L and line R. And right there, that's the proof, because all I need to show is that the intersection is going to be a single point. And remember, that line is in the plane, so therefore the plane's intersection is going to be just that one single point as well. Okay? All right, so there's your theorem for 3.2, okay? And we're probably going to use that in the near future, so keep that in mind. The next few things will be Postulate 7 over here. So this one, there's no proof in it, but rather it's just something pretty simple for the most part. Any 3 points lie on at least one plane. Any 3 points that lies on at least one plane. There's a second part to this, which says that any 3 non-collinear points lie on at most one plane. So let me do the second half right here, because I think that's a little bit something that's easier to grasp. If you have 3 non-collinear points, as we said earlier, right, there is exactly one plane that contains them, and you can see it because that plane is going to be this triangle, or be represented by this triangle, or maybe just a screen right here. So here's A, B, and C. And this is so long as the 3 points are non-collinear. Now, imagine the other case, because look at my first scenario. Now I'm choosing any 3 points. So what that means is I am no longer restricted to non-collinear points. I can choose 3 collinear points. And right there, if I say the 3 points are collinear, then you can now kind of see how that works. Because look, if I have a single line, then in space, there are infinitely many number of planes that are going to contain that line then. So here, let me just see if I can kind of draw it without having to butcher everything. So here you can see that there's one plane right there, okay? And then here, maybe I can draw a different plane using a different color. So here you can see a different plane right there. And then maybe I can have another plane right there, okay? But regardless, what's going to happen is there are infinite number of planes that are going to be intersecting with that line, or that's going to contain that line then. So that's what I mean by if you don't have the restriction of non-collinear points, then there are infinitely many number of planes that are going to contain them. But whereas if they are non-collinear, then there's only going to be at most one. So one says at least, one says at most. That's the easiest way to remember. And one is for non-collinear, and the other one is just for any points. Okay. All right. So here's the next one, Theorem 3.3. Now, this illustration right here, I just drew the picture of it. Here's a question. If you have a point that's not on a line, so here you see point A right here, and you have another line which we'll go ahead and call line L, how many planes are there that contains the two? Well, I would like to think that there is only one plane that's going to contain them. Okay, I would like to think that there's only one plane that contains them. So that plane is going to be, something like this right here, right? If you take a pencil and you take a single point somewhere, you can visually probably see that, yeah, if I put them all both on the table, that table is going to be the plane then. Okay, so there it is. The proof is that if there, sorry, not the proof, the conclusion is that there exists exactly one plane that contains the point and the line. Okay, so let's now think about the proof for this. Okay, let's go ahead and think about the proof for this. And this one is actually not very bad, because if you just kind of refer back to what we're saying, postulate number 7, I think we can actually come up with a proof very quickly. If you have a line, right, remember, by kind of like our formal definition of a line, what we can do is we can always pick 2 points on there. So what I'm going to do is I'm going to go ahead and say, let point B and point C be on the line. Okay, so I'm going to go ahead and introduce these 2 points. Here's point B and here's point C. Now, according to this picture, right, since A is not on line L, since A, the point, right, is not on line L, then we can conclude that A, B, and C are non-collinear. Okay, non-collinear. And right there, I think that's the key right there, because as soon as we say that we have 3 points that are non-collinear, then we can say by postulate number 7, the one we just talked about, okay, there exists exactly one plane that contains them, contains the point A and line BC. And right there, there's your proof then. Okay. All right, so hopefully, that's not too bad. Again, these proofs, they're not supposed to be very, very difficult, but, it does take a little bit of ingenuity, so, that's what I'm here for. All right, so here is the last theorem of this section right here, which I think is going to be very similar. If you look at the picture, well, I think you can kind of get an idea as to what you want. You have 2 lines that are going to intersect each other. Okay, you have 2 lines that are going to intersect each other. The question is, how many planes are there that contains line 1 and line 2? Well, if your answer is 1, right? If your answer is there is exactly 1, then you are correct, because you can see in the picture, right? You have 1 plane that's going to connect them. Imagine taking 2 pencils and then having them intersect each other. Then the result is that there should be only 1 plane that contains both of those lines then. Well, then here, the conclusion, right, is there exists exactly 1 plane that contains L1 and L2. And if you're wondering about the proof for this one, why don't I give this to you and maybe you can work it out. I'm going to go ahead and start by saying, hey, L1 and L2 intersect. The intersection between 2 lines is going to be most likely a single point, as we pointed out earlier. Let's go ahead and call that point A. Then what we can do is we can go ahead and say, hey, let point B be an L1 and let point C be an L2. And I think from there, you can probably see what's going to happen then. Okay, so use that as your setup. Let point A be the intersection of L1 and L2. Let B be another point on L1. Let C be another point on L2. Then what's the conclusion according to what we said earlier? Hint, hint, postulate 7 once again. Okay. All right, so here's the last item, postulate number 8. The intersection between 2 different planes is going to be what? Well, here, let me just draw an illustration of it. So here you have 1 plane right here. And then imagine this in 3D, right? So this is going to be called plane number 1. We'll call it plane P. Plane P. Lots of words, horrible. Okay, and then here we have another plane right here. We'll go ahead and call it plane, we'll call it M or something like that. M for Mr. Chan. Now, looking at what we have, right? When you have two planes that are intersecting each other, right? Imagine, like, say, if you take two pieces of paper and they intersect, what is the intersection going to be? Well, you could probably see it right there. It's going to be this line over here. So then the intersection is going to be a line then, okay? And that line, keep in mind, is not a line segment. It is a line that goes on forever. So that means it goes out this way, it goes out this way, because the plane also extends out in every single direction that you see that I could not draw because, you know, we're on a piece of paper. All right, so that should do it. Thank you so much for watching. I will see you next time. Have a good one.